So let's see. So the first assignment is due in class on Thursday. We will have a problem session here led by our friend Charlie Walden right afterwards on Tuesday's January. And Gopi will be holding his office hours on Wednesday from 1:30 to 2:30. Okay? And if we need some other office hours, well, I'll be available as well. We also have the other problem session on Friday after the chair's seminar. So there's lots of time for discussion. Okay, so if you can't make one of these, you can make something. All right? All right, so let's see. So last time we were talking about the idea of coherence, and particularly temporal coherence. Hold on a moment. Excuse me, folks. Thanks. All right, so we're talking about temporal coherence. And in particular, what we were looking at is how one measures coherence in an optical field based on interferometry. So this is our standard paradigm for thinking about interference. We think about two paths that interfere, classically in this case. Okay? And so if these are 50-50 beam splitters, then the output electric field is just at this port is just going to be equal to the superposition of those two with that phase in between. And the total intensity output out this port is given by the square of the complex amplitude. Now, as we discussed last time, in the case of what we might call natural light, light that is coming from stars, light that's coming from light bulbs, generally speaking, the electric field at any time we think of as a random variable. We don't know necessarily exactly what the field is at any time, and generally it will have lots of fluctuations, okay? And that could be occurring, for example, because the oscillators, say in the bulb, that are radiating are being bombarded by collisions with other molecules, which disturbs the phase. And so we don't know, for example, what the phase is at any time. It's a random variable. So we might ask about what is the average intensity coming out based on some model of the probability distribution of possible electric fields that could come out of that source. And that's something that you're studying for homework, right? So the electric field is a random variable, therefore the intensity is a random variable. We would say look at the average intensity at any time. And we have the interference terms, as well as the terms that have to do with the individual average intensities in each of the arms of the interferometer. And we talked about the idea of stationary statistics, meaning to say that any expectation that we have between two fields only depends on the relative time between those two fields, not the origin of time. So that's to say that the nature of the collisions is not changing as a function of time. So the statistics are stationary. So that's to say that the field is stationary, it's changing as a function of time, but the probability distribution from which we would draw a potential electric field is the same probability distribution at any time, okay? So that's what we call stationary statistics, and in that case, this would just this times itself star, and that should just equal to the expectation value of that at time 0 squared, since it's the same, we're looking at it at the same time. Same thing here, that's twice the intensity, so that's this term. And then we have these terms, which again only depend on the time difference in the end. Okay, so that's an assumption about the nature of the statistics. And so the intensity that we would see, the average intensity we would see out that output port would have then this form, okay? And we see that it depends on this key quantity here. This quantity is the autocorrelation function. That is to say, the correlation of the field with itself at two different times. And if they're very well correlated, we would say very coherent. If they're not correlated, if there's complete randomness between the field at some time, some other time, we would say it's incoherent. Okay? And so one way we could get that incoherence is, as we discussed, we might have a situation where instead of having an infinitely long wave train of oscillations of the field's phase is being randomly kicked due to these collisions. Okay? And you're studying that in homework, and what we see in that case is that the two-time correlation function will generally decay with time. So that where tau 0 here is the mean free time between collisions. Okay. And so under that model, the output intensity out the interferometer has this form. Okay, and if we plot that as a function of tau, which is the distance between the two arms of the interferometer over c, then that intensity has this form, which is to say the interference fringes don't go all the way from maximum of all the intensity going out that arm to minimum where there's complete destructive interference, but depending on the distance between the pads compared to, or the time difference that it would take light to go between these two paths compared to the time scale of the collisions determines the depth of the interference fringe, the difference between maximum intensity and minimum intensity. And when the arm difference is sufficiently long, then half the intensity would go out that port. Where would the rest of the intensity go? Out the other port, right? So if I were to sketch what the other port is doing, it would have an intensity pattern that looks like this. Right? So that if we have a big distance between the pads, and that distance is big compared to what we call the coherence length of the light, then effectively there's no interference. And in that case, half the light would go out port 1, and half the light would go out port 2. It's only when there is a well-defined phase relationship between those two pads that there is interference where we can get constructive interference. And all of the light would go out this path, and destructive interference, and none of the light would go out that path, for example, if it was a perfectly balanced interferometer, which we would see if the two arms of that interferometer were exactly equal with completely incoherent light, we would still see all of the light go out this way and none of the light go out that way, even if this light were completely incoherent. This is what we would call a white light interferometer. It's perfectly balanced. Okay. All right. So, now that was what we were talking about in the context of the coherence of light, and what we saw some features there having to do with random statistics. In this case, the statistics, the randomness of the field was due to classical randomness. Randomness that was because we had missing information about the nature of the trajectories of all the atoms in the gas. Yeah.
So for the random phase due to collisions.
Yep.
So for a certain period of time, it seems like the phase is not changing, right? What happened if that time was really, really low? Then everything would look like if we didn't have the ability to measure.
Sure. So if the time between collisions was short, very short, compared to the period of oscillation, well, then we wouldn't see any interference at all for anything more than a perfectly balanced interferometer, because this thing would just decay, right? So what we're assuming here is, in this picture, that the light is quasi-monochromatic.
Okay.
That is to say, there's at least a few periods of oscillation between. So the question is, how big is this decay compared to this? If the period of oscillation was much longer than the K length, then I wouldn't see any fringes at all. But this is a picture, and this is actually not particularly quasi-monochromatic the way I drew it, right? There's not very many oscillations. I mean, this picture isn't really quite consistent with this picture. But that's a good point. All right, so yeah, so what I was saying just a moment ago is here, this, the randomness that we see is classical randomness in a sense, okay? We're going to study in more detail later in the semester when that randomness is coming from the fact that there's intrinsic quantum randomness associated with the field. The field is described by a quantum state, and the quantum state might not be an eigenstate of the electric field operator, in which case, when we measure it, we don't have a definite value. We get some randomness, right? So this is what we might call quantum noise, as opposed to this is classical noise, classical statistical optics. They're interrelated, and we'll talk about that more over time. All right? But what we're discussing right now is something slightly different. We're talking, what we want to discuss a moment is, so here we talked about the light that was being generated by oscillators. And the coherence of the light was related to the coherence of the oscillators. Okay? So what we want to talk about is coherence in matter. Okay? And so ultimately what we really want to talk about is the quantum coherence in matter. But we're going to start with just talking about the classical coherence. Okay? So what do we mean by that? Well, we're talking, and it's exactly the same way we just discussed, we're talking about, say, oscillators. So the typical picture here is the Lorentz oscillator. I mean, this is extremely basic, but extremely important. You should really understand every last thing about this and have it completely under your belt. So what we're talking about here is thinking about the absorption and emission of light by matter, where we model that very simply as an electron that is harmonically bound to a nucleus. Okay? And so we think about this as an electron on a spring. Okay? And the spring has associated with it some restoring force, and there's some natural resonance frequency depending on the mass of the electron, square root of capital over M. And we're going to assume that there's some rate at which this oscillator damps. We'll come back to that in a moment. Okay? And that bound mass is being forced by an electromagnetic wave. So there's some electromagnetic wave that comes in with some, say, electric field. Let's just take it to be linearly polarized. Doesn't matter really. And that will force the electron. This has some mass, right? And so we can write down the most trivial Newton's equations that describe the motion of that charge, right? So the mass times the acceleration, let's say that the displacement of this electron from equilibrium is equal to the force on the electron. The force on the electron is going to be, well, there's the restoring force of the charge. There's the damping force, and that's just some kind of viscous-like force, right? Drag proportional to velocity. And then, in addition, there is the force that is exerted by the field on the atom, right? And that's the charge times the electric field at the position of the center of mass as a function of time. So that's Newton's laws. We could write that down. All right. So that gives us the trivial equation, the simple harmonic oscillator, damped simple harmonic oscillator. Right? So that's the position of the electron relative to equilibrium as a function of time. Now we'll take the electric field here. Now, of course, there's a little bit of sleight of hand here, which is, of course, this electromagnetic wave also has a magnetic field. So in principle, there is a Lorentz force. This force really should have another part to it. It looks like that, right? Now, we're assuming here that this is non-relativistic, that the velocities are very small, in which case the magnetic force is just tiny. So it's just negligible. But it's there, pretty small. Yeah?
Are you treating E as being positive, little lowercase the charge of the electron?
Little e is a positive number. Always. Anyone who does anything else is an idiot. E is a positive number. Okay. 1.6 something electron volts. Okay. All right. So, the electric field, here we'll just assume this to be monochromatic, okay? So it's linearly polarized in some direction. It's, let's say it's oscillating frequency omega, and there's some phase at the position of the atom. Okay, it could be K times R, whatever phase it is at the position of the atom. All right? So, and as we often do, we'll write this as the real part of E0 e to the minus I omega. And so this is the phase at the position. And this is what we sometimes call E tilde. Right, factor out e to the minus I omega t. So maybe I should write it that way. All right? Okay, so when faced with such an equation, we can easily solve for the steady state motion of the charge by just knowing that in steady state, we know that this charge will oscillate harmonically. At what frequency?
That's frequency of the field.
At the frequency at which it's driven. Not the natural resonance frequency. If I pluck it and let it go, well, of course it has natural resonance, but if I'm forcing a mass with harmonically, then it, in steady state, will oscillate at the frequency at which I force it. Okay? So we know that in steady state, so just look at, after time, a few gamma, 1 over gammas, we reach steady state, and the steady state, this is a function of time, is going to be generally oscillating at frequency omega. And any oscillating function can be written as a complex amplitude, e to the minus I omega t. Okay? So we can plug in this ansatz, plug that into here. Every time we see a dot, we replace it by minus I omega, and we get minus omega squared plus omega 0 squared minus I omega gamma. R tilde is equal to minus E over M E of R tilde. Okay, everyone see what I did? I just plugged in those ansatz. In the end, we take the real part, but right now we're just solving for the complex amplitude. And every time I saw a time derivative, I replaced it by multiplication by minus I omega. So, excuse me. All right, so now we can solve that for R tilde. And so what's going to happen? So this field will drive the system and it will oscillate, right? Which means that there will be an induced dipole moment. Okay? I mean, really this electron is sitting, inside the electron, this is really an electron cloud around the nucleus. We could just think about it as a separation of charge plus and minus, and that will induce a dipole moment. So there is an induced dipole moment. Electric dipole moment. D is a function of t, which again will be oscillating harmonically because the position of the electron is oscillating harmonically. So this itself is equal to the charge of the electron, which is minus E times R of t, which is equal to minus E, the real part of d tilde e to the minus I omega t, where d tilde is just that. So, putting that all together, what we see is that, plugging that in, I get E squared over M divided by minus omega squared plus omega naught squared minus I omega gamma times the complex amplitude of the electric field at the position of the atom. Okay? So I just solve for R tilde and plug that in. And what we see in this model of a spring which has a linear spring constant is what we call linear response. The electric dipole moment induced was just linearly proportional to the applied electric field. And that proportionality constant is this complex number here, which I call alpha tilde, which is the dipole polarizability. How able is it to be polarized? And it's equal to, in the Lorentz oscillator model, that. All right? So what we see in this linear response is that the induced dipole moment, if I plug that in, that's equal to the real part of alpha tilde times e to the minus I omega t. Right? By the way, it doesn't matter, I put the tilde up below or above, it's just that this guy already has a hat, so he needs some shoes. That's all. All right? So we can write that simply, if I express this, this is going to be equal to, let me plug this as E0 just to make it simpler to deal with, e to the minus I. Just plugging in the phase. This is, I'll take as real, because the phase is here. So this is equal to some real number plus I times some imaginary part. The real part of this times that, real that, is real cosine. So this becomes alpha, the real part of alpha tilde, E0 cos omega t minus 5r plus the imaginary part of alpha E0 sine omega t minus 5r. So this is a general result. That's always the case. Any function that oscillates like frequency omega can always be broken up into a piece that oscillates like cosine and a piece that oscillates like sine. Here, this is relative to this phase, so we're forcing this oscillator with a periodic forcing function that had some phase phi. There's a part of the response which is in phase, and that part of the response that's in phase is proportional to the real part of the polarizability. There's a part of the response that is 90 degrees out of phase and is thus sometimes called in quadrature. So that means 90 degrees out of phase. That's what 90 degrees is. Quadrant, where the term quadrature comes from. And the part of the response that is in quadrature with the force is proportional to the imaginary part of alpha. So that's one way to understand this imaginary part. Okay, let's look at it more carefully now. Let's look at what this function is. So we're going to look, as is a typical situation for atoms that we're interested in, is where we tune close to resonance. Okay? So we're going to look at the situation where, so let delta equal the applied force frequency minus the natural resonance frequency. Yeah.
One question before we move on.
Yeah.
In that, the big R, why is phase a function of big R?
Because of course, generally speaking, I might have a wave, right? So this could be, and it will be, generally, K dot R minus whatever phase R is, right? So that's the phase, the property. Where I am in space determines the relative phase because it's a propagating wave.
Okay.
Okay, so it depends where the atom is, what that phase is. Okay?
Yeah.
Good. All right, excellent. So we define this. This is known as the detuning. And there is not a universal agreement on the sign of this, but I will always take this convention that the detuning is the applied frequency minus the resonant frequency, not the other way around. Okay? So known as the detuning. You detune from resonance. You tune to resonance and detune away from resonance. And we're going to assume that the magnitude of this is tiny compared to omega naught. Okay? So we're going to consider that case where we're tuned very close to resonance, close in that sense. The tuning is very, very small compared to the natural resonance frequency. And we're also going to assume weak damping. This is near resonance. And we're going to assume that gamma, the damping rate, is tiny compared to the natural resonance frequency. All right, so this is weak damping. Okay. So we're going to just then look at this expression for alpha. Right, so this is E squared over M. We have minus omega naught plus delta squared minus, or plus omega naught squared minus I omega naught plus delta gamma, right? That's exact, just plugging in the definitions of delta. So omega is omega naught plus delta. And then this is approximately keeping terms only to lowest order in the small things. So we're going to neglect things like delta squared and delta times gamma and only keep the linear terms in those small quantities. Ignore the quadratic terms in those small quantities. And this then becomes approximately E squared over 2 and omega naught squared and omega naught minus delta minus I gamma over 2. So this is this as a function of delta. So same thing. Okay, doing that approximation. Now this form is something you will see over and over and over again. You should memorize it. Then what the numerator is, don't worry about that so much, but it's got this form in the denominator. This is known as a complex Lorentz. Let's look at its form. So this is a function of the detuning is equal to E squared over 2 and omega naught. And now I'm going to write this, rationalize it, multiply top and bottom by the complex conjugate to make this real in the denominator. And I get minus delta over delta squared plus gamma squared over 4 plus I. All right? So there we have, this is the real part. Well, that's this. So it's like the real part of alpha. And this is the imaginary part. Get that factored out, right? So let's sketch those things. So as a function of the detuning, which is the applied frequency minus the resonance frequency. What does the real part look like? Well, you should be able to sketch functions like this without your graphing calculator. The way you always do it is you look at the limits. How does it appear asymptotically? When delta is very, very small compared to gamma, then I can ignore that, and it just looks like that, a negative slope of the line with slope of -1, right? Well, it's got slope -1, but why did I draw it with a +1? Sorry. Looks like that. That was what it looks like. And then when it's big, when delta is big compared to gamma, then this goes away. And then it goes like 1 over delta. So it looks something like this. And then in between, it just has to smoothly connect. And that's how you sketch a curve. Everyone should know how to do that. Okay. Right? So this falls off like 1 over delta squared. I'm sorry, 1 over delta. What about this function? Well, it's, when this is small, it looks like a parabola. And then for big enough thing, it goes like 1 over parabola. Inverse of a parabola, so it looks like this. It falls off. 1 over delta squared. All right, so that's the real part of alpha, and this is the imaginary part of alpha. And this function has a full width at half maximum, full width at half max, which is what? This function. So when this thing falls off, when this thing is equal to gamma over 2, then I double the denominator, right? So this is gamma over 2, minus gamma over 2. The full width at half maximum is gamma. So the imaginary part of this function, this is a Lorentzian. Lorentzian function. That's what we sometimes call the complex Lorentzian. And the width of this function, these are algebraic tails, and that's not Gaussian algebraic. It's not falling off exponentially, it's falling off algebraically, like 1 over delta squared. This width is known as the line width. Now, these two terms, the real and imaginary part, are what's known as the dispersive response and the absorptive response. How do we see that? Well, we can see that in a number of different ways. Sometimes I'll say it's a slightly different one. Let me call it dissipative. Of course, it depends on gamma, which was related to the friction in the system, right? If we didn't have gamma, we would have friction. In that case, of course, the dipole would just keep, if we didn't have any dissipation, you force it, and would just keep growing and growing in amplitude. You would never reach steady state. You don't have friction. All right, so let's look at that. Well, one way to think about this is the following. Let's look at a collection of such a gas of Lorentz oscillators. With density and oscillators per unit volume. Okay? So let's think about the propagation of light through this gas. Well, what's going to happen is the gas is going to both phase shift the light because the re-radiated electric fields are not necessarily in phase with the input field, which leads to an index of refraction. It's also going to absorb some energy and scatter it, so that it will attenuate the field, right? So how would we describe it? Well, we can describe that in a simple model with Maxwell's equations. So let's look at the wave equation. It describes that. So we have the equation for the electric field with sources, and those sources are related to the polarization density. This is the dipole density. Right? C squared. And it's got, in this case, so the dipole density is the number of dipoles per unit volume times the dipole moment of each oscillator. And this is then equal to, again, there's a complex amplitude. So this could be equal to the real part of n e tilde e to the minus omega t at the position of the dipole. So now I can plug all that in, again with the electric field in that form, and I'm going to get delta squared plus omega squared over c squared e tilde is equal to minus 4 pi omega squared over c squared times n times d tilde, but d tilde is the polarizability times d tilde. Okay. So what I see then is that the equation of motion for the wave propagating as a function of position is equal to omega squared over c squared times the index of refraction, which is complex. And the complex index of refraction is equal to 1 plus 4 pi times the density times the polarizability. And if you're so inclined, 4 pi is equal to 1 over epsilon naught. In a form you might be more familiar with it. Okay? So this is the complex index of refraction. Now this Helmholtz-like equation has plane wave solutions. So that would say a plane wave solution to that would be, say, propagating in the z direction, would be some polarization e to the I k tilde z, where k tilde is the complex wave number. Remember Maxwell's equations and waves, right? index of refraction. And so what this says is that if I write this as a, let me call K prime the real part and K double prime the imaginary part, then this is equal to E naught, e to the minus the imaginary part, e to the I K prime T. So the imaginary part, assuming K double prime is a positive number, corresponds to attenuation. And the real part to the phase of the wave. Let's look at that more carefully. So, K prime is equal to N prime, see, and K double prime is N double prime. Okay. N is the square root of 1 plus 4 pi the density of dipoles times the complex polarizability. That's the complex index of refraction, right? Now, in this model that I've sketched here, I assumed all the dipoles acted independently. I didn't in any way say one dipole was affected by the electric field associated with the nearby dipole. That's only true for a very dilute gas. Okay? Otherwise, they're what we call local field corrections. So this only makes sense, this solution only makes sense for a dilute gas. And if this is a dilute gas, then this is a small number. So this is approximately 1 plus that. That's just using the binomial expansion for square root 1 plus a small quantity is 1 plus a half the small quantity, right? So what that tells me is that the real part, n prime, is equal to 1/2 plus 2 pi n, the real part of alpha, and n double prime is 2 pi n, the imaginary part of alpha. Okay? So, what that tells me, look, coming back over here, is that it is the imaginary part of alpha that is associated with the attenuation, and it's a positive number, right? The imaginary part is that Lorentzian. The imaginary part of alpha is associated with the attenuation of the field, and the the real part is associated with dispersion, the phase shift, right? So what we have is that the electric field e to the I 1 plus 2 pi and real part of alpha omega over c times d e to the minus 2 pi and imaginary part of alpha omega over c. So the imaginary part, the dissipation, corresponds to removing energy from the field. So the field, electric field, the intensity, which is the square of the field, decays. with a decay constant, A, that depends on, is proportional to this. All right, now why is that energy decaying? It's decaying because there is work being done on the charges by the fields. So if energy is leaving the field, it's because it's being absorbed by the matter. Energy that leaves the incident field is absorbed by the matter. So, how can we think about it? Well, the reason energy is being absorbed is that the field is doing work on the charges. Okay? And the rate at which it does work is what?
Like in regards to the homework, we would do that the F dot B.
That's what it is, right? The rate at which a force does work on a mass is F times V, right? So, and the force is the charge dotted into the velocity, which is r dot, which is equal to minus the dipole dot dotted into the electric field as a function of time. Okay? So now, if I look at this more closely, we can understand why it is the imaginary part of alpha is the part of the dipole response that's associated with absorption. Let's recall what we said here was that B is the real part of alpha B, right? Which is equal to what we said here was the real part of alpha, E0 cos omega t minus phi, plus the imaginary part of alpha, E0 sine. That was the part that oscillated in phase and in quadrature. So, d dot I'm sorry, this is not minus. Excuse me, because the dipole, pardon me. D dot dotted into E. Remember, E is E0 cos omega t minus phi. So I take the derivative here, and I get minus omega, the real part of this, E0 squared cos squared, no, cosine times sine. So derivative of this is sine minus omega cosine. And the derivative of sine is cosine. So if I look at this now, time averaged, because of course there's many oscillations, I want to know what it is time average. So they average this over time. The average of sine times cosine is 0. And the average of cosine squared is a half. So this time average work is a half omega, the imaginary part of alpha, d0 squared. This is the rate at which the fields do work on the charges. And what we see is that's proportional to the imaginary part of alpha. And it's because it's in quadrature. You see, you need to do work, you need to push on the charges. If they were in phase, on average, you get it work back, and you put it in, you get it back. It's when it's 90 degrees out of phase. So it's that the current, which is the derivative of the position, which is the velocity, is 180 degrees out of phase, that I get ohmic damping, and thus absorption in the field. Now, what that says, going back to this picture, is that the range of frequencies at which I drive the system, which I get a large amount of absorption, depends on gamma. Only when I am detuned within this range, which is the line width of the absorption, do I get substantial absorption. If my detuning is big compared to gamma, so I'm in the wings here, I get very little absorption. Now I still might get some dispersion, because the dispersion only falls off like 1 over delta, whereas this falls off like 1 over delta squared. Obviously when I'm very far detuned, well, they barely interacts because it's so far from resonance, it doesn't do anything. So the gamma here is what is sometimes known as the absorption line width. All right? Now, physically, where is this coming from? Well, that depends. Depends on what's going on in the system. As we just discussed, one of the ways I could damp an oscillator is due to collisions. So the very same mechanism that I just discussed at the beginning of this lecture, reviewing what we did last week, is one mechanism for damping. So we're studying this in homework. I'm going to give you a simpler model than the one you're studying in homework that can show you how we can see that collisions lead to damping on average of the oscillator. Okay? Average over an ensemble average of many oscillators. Well, one way to think about it is let's take this. I'm going to look at what was called the phase diffusion model. So let's imagine that what I get is that, let's say that the dipole gets a random phase plus or minus phi1 every interval tau. Okay, so the phase starts somewhere and then it gets kicked phi1 to the right or to the left, to the left, to the left, to the right, to the left, left, right, 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 left, left. That's a random walk, right? And so what we would say in that case is that after a time t, so that's t over tau naught kicks. That's very large. The probability of seeing some phase would be what? Assuming a random walk. It's a Gaussian, right? And that Gaussian has, so this will look like the square root of 2 pi some variance at time t, e to the minus phi squared over 2 delta phi squared. It's a Gaussian. And what is delta phi for a random walk?
So just to clarify.
Yes,
that
please.
Delta is now the change.
It's
not-
the variance associated with this Gaussian distribution. So what I want to know, so the idea here is that I start with some phase, whatever it is, and it's getting a kick, getting random kicks. So now the phase is not a definite value, it's a random value. But the particular phase I will see, I will find with some probability, and if I want to make Keith happy, I'll make it a small p. It's picked out of that probability distribution. It's a Gaussian probability distribution that has a certain variance, delta phi squared, which we know from the theory of random walks is a Gaussian, and the variance grows linearly with the number of kicks. So the variance here, I get each kick is delta phi and times n kicks, and n is t over t.
Okay.
Okay, so the phase is diffusing. That's to say what the value is. We don't know what it is. It's diffusing over the unit circle until eventually it has completely random phase. The longer the variance will grow with time. Yep.
So that phi1, that's just a phase, so it's not a unit circle, right?
So this is just it's assumed to be that phi1 is very small compared to 2 pi. Okay, so this is a slightly different model than the one that you have for homework that we discussed earlier, where we said there's where I didn't fix the kick. This is saying that at every time interval tau naught, I get the same magnitude of the kick, 1 milliradian, either plus or minus, okay? And I'm just asking if after some amount of time, given random kicks forward or back, the phase will diffuse over the unit circle with this probability distribution and this variance. Okay, so what that would say then is that the average dipole moment would be given by the integral over the probability of having a certain phase times the whatever the amplitude of that dipole is with whatever phase it has, e to the minus omega t. Okay? So if I had a definite phase, this is the complex. This would be the dipole. It would have some phase, I don't know what it is. It has some amplitude and oscillates like this. But now I don't know what the phase is. So I'm going to average over all possible phases, weighted by what the probability of the phase is. Okay. So this is the average dipole. Okay, you plug that in. Well, this is nothing more than the Fourier transform of a Gaussian. So what we would see in this case is but with the inverse here, right? Because when you Fourier transform, you get the inverse. So this goes in the numerator. And so this becomes yeah.
Is it the Fourier transform evaluated if the transform variable equals 1? Because usually I expect like an e to the I k phi times the thing I'm transforming. Here it looks like there's only an e to the I phi.
I'm integrating over phi. Phi goes from 0 to
I
pi.
expect the like transform variable. to
Well, the
be
transform
similar.
variable in this case is phi. So this
That
would
means
look,
the variable that it's transformed into.
well, in this case, so if you look for it, in that case, it's t. So let's plug that in. This becomes so I have to do this integral. So I just plugged in here, I forgot about the 1 over square roots. So this is just, I plugged in, this was the Gaussian function, and I integrate this with respect to this phase. What it does is it flips that.
Yeah.
Right? Now you could say, as you say, the transform variable is 1 in that case, but it's just that integral. Notice what we see here. What we see is that this thing is decaying with a gamma that depends on the rate of collisions and the phase step per collision. So this is known as collision broadening. That is to say, if I have a line, an atomic line that has a certain Lorentzian, if I increase the pressure in the vapor cell, then I'm going to broaden the line. That's sometimes known as pressure broadening, because there are more collisions. Okay. Collision or pressure broadening. Now, in this case, the electromagnetic energy, where did it go? Well, it went into heat, because we have collisions, more randomness, heat in the kinetic energy of all the molecules. Okay? So that's what the dissipation occurred in that case. But what if we had just one lone Lorentz oscillator that was I thought about as a trapped atom in an awesome vacuum, super duper awesome, the most legit vacuum you have, right? And there's no collisions, or none that I ever care about. What would happen in that case? Would I have an infinitely narrow line width gamma in that case? No. There's always some fundamental, we call the natural line width, the intrinsic natural line width of the system. Now, in this case, what is the mechanism by which energy would be dissipated if there were no collisions?
Radiation.
Radiation. So this thing will oscillate, and it will make an electric dipole, which radiates a dipole pattern. And that radiated field carries away energy. It's sometimes known as radiation damping. So radiation damping is a fundamental source of dissipation. And so there will be what we call the fundamental or the natural line width of the system that is due to radiation damping. And that's one of the things we study for homework. All right, very good. I guess we will stop there because we're 2 minutes. Maybe we have just a few minutes. I'll just introduce just the beginning of where we're headed from here. So this was our classical model of the coherence. What we see here, one thing to notice is that we have coherence in matter had to do with the damping of the electric dipole, which we could look at in the same way that we looked at or I could average this, or instead of thinking about it like this as we did before, as a two-time correlation function. The correlation of the complex dipole moment with itself at two different times determines the coherence in the oscillating dipole. Now, in electromagnetic theory, the radiated field is proportional to the dipole. So the coherence in the dipole translates into the coherence of the radiated field. And that's what we just studied, right? We looked at, we said, well, let me imagine we have these oscillating dipoles, and depending on that, they determine whether or not the field is. This picture is completely classical. It's saying that there is a part of the field that radiates due to a source. However, quantumly, there is a part of the field that's not due to the source at all. That's due to the intrinsic quantum nature of the field, the vacuum. So the true field that we will see, the total field, will be the source part, the radiated part, plus vacuum, which is quantum. Now, the relative contributions of this versus this, as we will see, depends on how strongly we are driving the system. If we are weakly driving a quantum atom such that it has linear response, this is negligible compared to this, as we will see. And in that case, we should think about it just like a Lorentz oscillator. That's to say, light comes in, drives an oscillator, and it re-radiates. And the scattered light that's scattered, that fluoresces from atoms, is just this classical picture. It's not, I go into the excited state and then I spontaneously emit. It's the wrong picture. It's what we would call elastic scattering. Keep that in mind, because we're going to revisit that a little bit later in the semester. All right? So to be continued, we'll pick this up on Thursday. So have a little break. At 2, Charlie will be here to discuss the homework for those who discuss it.